We eat eggs in many forms, but the method is usually the same. We break the egg, use what is inside, and throw away the shells. But do you know the chemistry of these shells? Well, eggshells are largely composed of a crystalline form of calcium carbonate, which is an example of natural precipitation. What other precipitation reactions can occur in nature? Meet me in the studio to find out. Hello and welcome. I am Devabrata Goswami and you are watching Chemistry 11. But before we begin, let's take a look at the agenda for today. In today's episode, we will learn about the common ion effect in solutions and the criteria for precipitation and buffer solutions. After the learning part is over, we will head straight to the exam decoded segment. All of you know that chemistry is all about experimenting. So let's head straight to the lab to understand what the common ion effect is all about. Take a solution of silver chloride and water in a test tube. Now add a solution of sodium chloride to this solution. Watch what happens. Can you see a white precipitate form? This is silver chloride. The question is, why did silver chloride precipitate out? Keep thinking. The answer is quite simple. Silver chloride precipitated out due to the common ion effect. Let me explain. We know that silver chloride is a sparingly soluble salt. I hope you remember, sparingly soluble salts are those salts which have a solubility of less than 0.01 molar. So, an equilibrium is established between the solid silver chloride and its ions. Now, when a strong electrolyte like sodium chloride is added to it, it ionizes completely. Notice that both sodium chloride and silver chloride have a common ion, the chloride ion. So, when sodium chloride is added to a solution of silver chloride, the concentration of chloride ions increases in the solution. Therefore, according to Le Chatelier's principle, the equilibrium shifts to the reactant side and hence some of the solid silver chloride precipitates out. Do you remember Le Chatelier's principle? No? Let me repeat it for you then. The Le Chatelier's principle states, if a system in equilibrium is subjected to a change of concentration, temperature or pressure, the equilibrium shifts in the direction that tends to undo the effect of the change imposed. Now, let's try to define the common ion effect. If to an ionic equilibrium of AB giving A plus and B minus, a salt containing a common ion is added, the equilibrium shifts in the backward direction. This is called common ion effect. We can see that here the common ion is A plus. So, the dissociation reaction will shift in the opposite direction. That is, the ionization becomes suppressed. So, we can say that if a strong electrolyte is added to the solution of a weak electrolyte and they have a common ion, the ionization of the weak electrolyte is further suppressed. Similarly, if a soluble salt having a common ion is added to the solution of a sparingly soluble salt, the solubility of the sparingly soluble salt further decreases. Common ion effect also plays an important role in our labs. Can you tell me what role does common ion effect play in labs? Keep thinking while I get back after the break. Welcome back. I am Devvrata Goswami and you are watching Chemistry. Before the break, I had asked you what is the role played by common ion effect in labs. Let's take a look. In labs, common ion effect helps in detecting cations. Let us understand this with the help of an example of group 2 cations. I have taken copper sulfate solution in a test tube and have added dilute hydrochloric acid to it. Remember that copper ion belongs to group 2. Now let us see what happens when I pass hydrogen sulfide gas through the solution. Can you see a black precipitate appear? Why does the black precipitate appear? Well, hydrochloric acid is a strong electrolyte and hydrogen sulfide is a weak electrolyte. Now, due to the presence of a common hydrogen ion, the ionization of hydrogen sulfide is suppressed and the concentration of sulfide ions in the solution decreases. But while group 2 sulfides precipitate out, the higher group sulfides, which have higher solubility product than group 2 sulfides, do not precipitate out, so the black precipitate we saw was of copper sulfide. We just saw the precipitation of group 2. I am sure you know that precipitation reaction involves the formation of an insoluble compound that separates out and settles. You must have heard about the formation of stalactite and stalagmite in caves. They are formed by a precipitation reaction. Now, how can we determine the possibility of formation of a precipitate by comparing the ionic product and solubility product values? Keep thinking. It's actually quite simple. I hope you remember. Solubility product is defined as the product of the molar concentrations of the constituent ions, each raised to the power of its stoichiometric coefficient in a saturated solution. Ionic product is also the same, but it corresponds to all kinds of solutions. An important point to remember is that precipitation will occur only when ionic product exceeds solubility product. Remember in the beginning of the show, we had talked about the composition of a hen's eggshell? Well, it is largely composed of calcite, a crystalline form of calcium carbonate. Before a hen lays its eggs, the shell forms inside its body via a complicated series of precipitation reactions. The hen's diet includes highly colored compounds like corn husk. Such compounds form a colored precipitate with the calcium carbonate of the shell during shell formation. This is seen as the eggshell's color. Do you know that the formation of kidney stones is also based on precipitation? Kidney stone is a precipitate often of calcium ions and oxalate ions. High intake of food rich in calcium or oxalate ions causes a rise in the concentration of either ion or both, and this causes the ionic product to become greater than solubility product. Hence, the precipitation of calcium oxalate as kidney stone takes place. Interesting, right? Let's move on to another interesting bit of information now. All of you might have seen car bumpers, and you all know that they serve as buffers for passengers as they absorb the energy of an impact. the word buffer is usually used in the context of absorbing a shock. Similarly, in case of solutions, a buffer solution refers to a solution which resists a change in pH caused by dilution or the addition of limited amounts of acid or base. Human blood is an excellent example of a natural buffer solution. Recall that pH is defined as the negative logarithm to the base 10 of the hydrogen ion concentration. Buffer solutions are of two types, simple buffers and mixed buffers. Simple buffers are the solutions of salts of weak acids and weak bases, while mixed buffers are the mixture of two components. Ammonium acetate is a good example of a simple buffer. Mixed buffers can either be acidic or basic in nature. Acidic buffers contain equimolar quantities of a weak acid and one of its salts with a strong base. An example would be a mixture of acetic acid and sodium acetate. Basic buffers contain equimolar quantities of a weak base and one of its salts with a strong acid. An example would be a mixture of ammonium hydroxide and ammonium chloride. That was quite a bit to retain, right? I am sure you have had some doubts, like this caller who has a very important question to ask.
Hello everyone, this is Rakhi and my question is, why are buffer solutions important?
First of all, thank you for the question. Buffers are very important for chemical and biological systems. The pH in the human body varies greatly. For example, the pH of blood is about 7.4, which is alkaline, whereas the gastric juice in stomach has a pH of about 1.5, which is acidic. These pH values are crucial for proper enzyme function and the balance of osmotic pressure. To maintain the pH, buffer solutions are necessary. I hope that clarified your doubts. For more questions and doubts, log on to www.topperlearning.com. But now it's time for a short break. I will meet you in a bit with exam decoded. Welcome back. I am Devabrata Goswami, and now it's time to take a look at this topic in the light of exams. But before that, let's do a quick revision. Today we learned that if to an ionic equilibrium a salt containing a common ion is added, the equilibrium shifts in the backward direction. This is known as the common ion effect. Apart from this, we also learned that precipitation occurs only when the ionic product exceeds the solubility product. Lastly, we learned that buffer solutions resist a change in pH caused by the dilution or the addition of limited amounts of acid or base. And they are of two types, simple buffers and mixed buffers. And now that we have buffered ourselves with knowledge, it's time to look at exams straight in the eye with exam decoded. Welcome to exam decoded. Ever wondered how the most successful students score those top marks? Well, stop wondering, because exam decoded will give you all the tips you need to become a topper. To test how well you have understood today's topic and to help you build your confidence, here is the rapid fire round. The rules are simple. I'll ask you 5 questions. You will need to respond to each within 5 seconds. Give yourself a mark for every correct answer and we will tally the scores at the end of the round. Ready to face the first question head on? Buffer solutions resist any change in its pH. True or false? The answer is true. Now for the next one. A mixture of acetic acid and sodium acetate is A. Basic buffer, B. Acidic buffer, C. Simple buffer, D. Salt buffer. The answer to this one is B. Acidic buffer. Here comes the third one. A shift in equilibrium is caused by the addition of a substance that provides ionic species already present in the equilibrium. True or false? The answer is true. Here is the fourth one. This one is difficult, so pay attention. Any sparingly soluble salt, AB, will get precipitated by the addition of A, DB, B, CD, C, C, D, FC. The answer is clear. It is option A, DB, since DB has an ion that is common with AB. Now for the last question. Here it goes. Precipitation occurs if ionic product is A. less than solubility product, B. more than solubility product, C. equal to solubility product, D. none of these. The answer is B. Precipitation occurs if ionic product is more than the solubility product. Had fun? If you got most answers right, I am sure you must have had fun. Here is your scorecard. So rate yourself honestly and base your preparation accordingly. If you got all questions correct, then you are a high flyer. If you got more than 3 correct, then you are an achiever. But if you got less than 3 correct, then you need to work a bit hard. But don't worry, log on to www.topperlearning.com for any help you may need. Now, let's see the kind of questions that come from this topic. Well, this chapter is from Unit Equilibrium. It has a weightage of 6 marks and is critical from exam point of view. Questions based on conceptual ability are usually asked from this topic. The questions asked are usually very short or short answer type questions for 1 to 2 marks. All of you are aware how important presentation skills are. It isn't only important to know the answer, knowing how to present it is equally important. So take a close look at how this question is answered. Why is hydrogen sulfide gas used in the presence of hydrochloric acid to detect group 2 cations? If you get a question like this for 2 marks, here is how you would be expected to answer it. Hydrogen sulfide gas in presence of hydrochloric acid is the group reagent for group 2 cations. Group 2 cations are precipitated as sulfides in acidic medium. Writing this much will fetch you 1 mark. Hydrochloric acid is added to suppress the ionization of hydrogen sulfide so that only group 2 sulfides precipitate out and not the higher group sulfides. Writing this reason will fetch you another 1 mark. So now there is nothing that can stop you from scoring full marks. To facilitate your scoring further, we invited an expert to give you some more inputs pertaining to this topic.
If to a solution of a weak electrolyte, a strong electrolyte having a common ion is added, then the suppression of the weak electrolyte occurs. Also, precipitation occurs only when ionic product exceeds the solubility product. Another key point to remember is action of buffers. Buffers are the solution which resist any change in the pH. That could be due to dilution or due to addition of a acid or a base. Example is acetic acid with sodium acetate. Another combination could be ammonium hydroxide with ammonium chloride. From examination point of view, numericals are generally asked from common ion effect. Also, in the practical exam, salt analysis is based on the common ion effect. Therefore, student must prepare both for theory as well as practical on the common ion effect topic.
This brings us to the end of this show. But I suggest you keep thinking even after I leave. So here is an interesting question for you. Why are antacids used during acidity? Try and seek the answer for yourself and share it with your friends. I will meet you again with another episode of chemistry. Till then, goodbye.